Hi everyone, we're going to finish section 4.6 by graphing transformed cosecant and secant functions. In the beginning, let's start with y equals sine of x, that classic odd sine wave. Now remember, how do you graph y equals cosecant of x? Y equals cosecant of x, it's the up u down u graph. And we would have VAs at x equals 0 and x equals pi, for example. Now, what happens if we were to put 2's in front? Y equals 2 sine of x. What would happen? The amplitude doubles. We have a vertical stretch by a factor of 2. What if we do the same over here and put y equals 2 cosecant of x? Again, we get a vertical stretch away from the x-axis by a factor of 2. And once again, the purple graph attaches itself like a parasite or a remora to the green guide graph, the sine graph. What if we put a 3 in front of the x? We get a more hyper sine wave. The period is cut down to a third. What if we put a 3 here for cosecant? Again, the purple graph attaches like a parasite. It's the same up u down u pattern. And the max point for the green graph here matches up with the min point for the purple graph. Same for here and here. Over here, max on purple is min on green. Same for here and here and here. What if we substitute x with x minus pi over 4? That leads to a horizontal shift. Well, if you do the same for the cosecant equation, same thing. The purple graph attaches like a parasite. What if on the green graph, for sine, I put a big old +1 at the end? That raises the graph by 1 unit. How about the purple graph? +1. So take a look at this. Just by replacing sine with cosecant, if I can graph the corresponding sine equation, then I can basically play the whole up u down u game to graph the corresponding cosecant equation where I replace sine with cosecant. The same properties hold for cosine and secant. So basically this tells me that if I wanted to graph a more general cosecant function like this, the key thing is to graph the corresponding guide graph, in this case with sine. And if I know how to graph the version with sine, then I play the whole up u down u game to get the graph I want for cosecant. And again, the same goes for cosine and secant. So being able to graph the guide graph, the sine graph here, is really helpful in graphing the graph we actually want. All right. So in general, how do we graph something of the form y equals a non-zero number, times cosecant or secant of a linear function of x, all plus d? For example, how do you graph something like this? Use the frame method, or not, just give me all the info, to graph one cycle of the graph of y equals -3 secant of 4x plus pi, all plus 2. Again, the critical thing here is to be able to graph one cycle of the guide graph when you replace secant with cosine. Well, very fortunately, we've already done that. In section 4.5, we graphed one cycle of the corresponding guide equation, y equals -3 cosine of 4x plus pi, all plus 2. And this gives us an opportunity to review this example, which we had to rush before. We're going to review the frame PCAPIA method for this cosine equation, and then we'll show how to get the secant graph from the cosine graph over here. Let's review PCAPIA. All right, for this cosine function or equation here. Now, PCAPIA, the frame method. The first P is for pivot, which is my term, pivot, but this corresponds to P comma D, the point that the origin moves to. The pivot is the point P comma D, the point that the origin moves to. Point the origin moves to, basically. P is the horizontal or phase shift. P is the phase or horizontal shift. And D is the vertical shift. Oops. I'll retype this. P is the phase horizontal shift. D is the vertical shift. Okay. Now D is very straightforward. We can just grab this constant term over here. That's D. That's the vertical shift. The phase shift, so D is 2. The phase shift or horizontal shift, that takes more time. You can either use a factoring method or set this equal to 0 and solve for x, which I think is easier. But if you want to use the factoring method, you take the argument here, 4x plus pi, and you factor out a 4. B. This is B, actually. B is 4. You factor out B. If B is negative, you absolutely have to factor out at least a negative 1. But here we have 4x plus pi. We factor out B, the 4. When you factor, you divide. We have 4 times the quantity, x plus pi over 4. And what is x plus pi over 4? It's x minus negative pi over 4. The phase shift P is negative pi over 4. You do a sign flip from here to here. The phase shift is negative pi over 4 from the factoring technique. Again, if that seems confusing, the easier way to do it is to take this argument, 4x plus pi, set equal to 0, and solve for x. Subtract pi, we get 4x equals negative pi. (4x equals negative pi), and then divide both sides by 4, you get x equals negative pi over 4, which again gives us the phase shift. Now, you have the right to add or subtract the period any integer number of times. Now, if this value of x were extreme, like a million radians or something, then we would probably want to use the period to knock it down. Keep subtracting the period until you get something as close to 0 as possible. Technically, the phase shift is the horizontal shift, the most appropriate horizontal shift that's closest to 0. But in practice, I will take any horizontal shift that'll work. But technically, the phase shift is supposed to be the horizontal shift, the appropriate horizontal shift that's closest to 0. If necessary, add or subtract the period an integer number of times. Here, negative pi over 4, that's as close to 0 as we can make it, as it turns out. The period turns out to be pi over 2, and we're not going to get anything better. So we're going to take negative pi over 4 as our phase shift, our horizontal shift. So the pivot, the point that the origin moves to, is P, the phase shift, negative pi over 4, comma D, 2, the vertical shift here. We knew D was 2. That's the point that the origin moves to. All right. Now for the frame method, the pivot corresponds to the left center point of the frame. Only tangent puts it at the center point. For every other trig function, the pivot goes at the left center. Now, we have here a cosine function on the right side, function of x. Now, notice that b is positive. That's important because if b is negative, you better take care of that right off the bat using the even property for cosine. And you might have to do some factoring in here. But since b is positive 4, that's not a problem. But first of all, we need b to be positive. We know cosine is over here, and we have A is -3, which is negative. So we have cosine and A being negative. What kind of cycle does that correspond to? Cosine and A is negative, given that B is positive. Normally, a cosine cycle looks like that, but since A is negative, we flip it around, and it looks like this hill or pimple. That's the cycle shape we want, the C in PCAPIA, A at the end. What about the amplitude? Cosine graphs have amplitudes. Is the absolute value of A, the absolute value of -3 is +3. That's the half height of the frame, or in this case, the graph. The period, which is the second P in PCAPIA, that's period. For everyone except tangent and cotangent, it's 2 pi over B. We assume B is positive. What was B? Well, B, remember, is the coefficient on X. Again, if B were negative, then fix it so that B is positive. But B here is +4. It's the coefficient on X, and it's positive. So the period is 2 pi over 4. That simplifies to pi over 2. But remember, we're going to use the increment more directly. That's always 1/4 times the period. 1/4 times pi over 2 is pi over 8. So let's use the frame method. Here we go. PCAPIA. PCAPIA. I'll put that here again. PCAPIA. First P for pivot. Where's the pivot? It's right here at the left center point. In this case, the point is not actually a point on the graph, on the pimple, the hill. Now the pivot is at the left center. We found that the pivot was at -pi over 4, 2. P here, D here. That's where the origin moves to. C for cycle shape. It was this hill. We get these 5 key points. Min point, inflection point. It's no longer an intercept. It's just an inflection point. Max point, inflection point, min point. A for amplitude. The amplitude was 3. 2 plus 3 is 5. 2 minus 3 is -1. These are the y coordinates of these key points, these quarter points. The P was for the period, but what we use directly is the increment, I for increment. It was pi over 8. Over here, we start at -pi over 4, but the increment is pi over 8. The increment was pi over 8. It was 1/4 of the period. Remember, we calculated that up here. It was 1/4 times the period, pi over 8. So let's put this in terms of eighths. Remember that 1/4 is 2/8, so -1/4 pi is -2/8 pi. We can write this as -2 pi over 8. If we put things in terms of eighths, it makes the addition much easier. We're going to keep adding the increment to get each new coordinate on this grid, this frame. A common denominator helps. -2 pi over 8, which is the x coordinate of this point here, -2 pi over 8 plus 1 pi over 8, the increment, is -1 pi over 8. This is simplified. -1 pi over 8 plus 1 pi over 8 is 0. We're very thankful for that. In fact, we could use symmetry now to get pi over 8 over here and pi over 4 over here. Or you could just keep adding pi over 8. 0 plus pi over 8 is pi over 8. 1 pi over 8 plus 1 pi over 8 is 2 pi over 8. That simplifies to pi over 4. Where does the period come in? The width of this cycle is the period. Pi over 4 minus -pi over 4 is pi over 2. and that's the period. The period is the width of the cycle. It's pi over 2, which is what we figured out up here. The period was pi over 2. And that's where the period is embedded in the graph. It's this right x-coordinate minus this leftmost x-coordinate. It's the width of this cycle. Do not put the period here if the number here is not 0. All right. PCAPIA, that last A. Let's add that to the notes. PCAPIA, A for axes. Superimpose the coordinate axes. The equation of the x-axis is y equals 0. So we want to put this x-axis between y equals -1 and y equals 2. Again, I won't get a ruler, but make sure that the x-axis is between these two line segments on the frame, between the -1 and the 2. And put the x on the positive end, the right end, not the left end, the right end. A lot of students forget that. The equation of the y-axis is x equals 0. Luckily, we have 0 right here. The y-axis is right here, but the y on top in the positive end, not the negative end. For some reason, a lot of students like to put the x here and the y down here. No, you put the x to the right, the y on top. And there, you have one cycle for that cosine guide graph. But we're not done. Because remember, the original problem was a 4.6 problem. We wanted to graph one cycle of that. But once you get this, you're 80% of the way there. All right, now here I'm squishing the frame a bit. The frame here was kind of big. I'm going to squish it. So here's the frame, this thinner rectangle. It's more squat, it's shorter. This hill is the same as this hill. I'm just squishing it. So based on the red graph and the frame, how do we graph one cycle of the original secant graph? This is the actual secant graph I want. The VAs go through these midpoints, these inflection points. They're no longer intercepts on this red hill, but they're still inflection points. So you put a purple VA through here and through here, through the inflection points, these middle points on the red hill. And then you go up U, down U. Here we only have room for half of a down U until we hit this VA. Here we can get a full up U between the two VAs here. Over here to the right of this VA, we only have room for half a down U. But together, in purple, we have one complete cycle for that secant function, and we have the VAs that are in the vicinity. And lo and behold, together with these coordinates, these axes, these labeled axes, if you look at the purple graph, together with the purple VAs here, we have a graph for one cycle of that secant function in purple. And the guide graph helped a whole lot. We pick up a max point for the purple graph, a VA, this min point on this U, another VA, and another max point over here on this down U. Yes, these points down here are max points for these purple pieces, these pieces of down U's, and this point on the y-axis is a min point for this up U piece. So this point up here, this y-intercept, is a local minimum, actually, a local minimum point. And these points here are local maximum points, even though they're technically lower than this point here. So it's all about the guide graph. If you can graph one cycle of the guide graph, then to graph one cycle of the corresponding cosecant or secant graph, put VAs through the inflection points for the guide graph, and do your up U, down U game. And that's that. That was a big adventure. Next, in 4.7, we'll look at inverses for these trig functions. Until then.